Hey, my name is Seth Adams. This is Lab 4 for Physics 2 Magnetic Braking with Faraday. So the purpose of this lab is to make observations and record data of a magnet falling through a conductive tube of aluminum foil. We need to model the experiment computationally and then compare the measured data and results with the computational predictions. For the results of this, we got an experimental fall time of 1.304 seconds with a computational fall time of 1.044 seconds. The physical concepts we used in this lab are the Biot-Savart law, Faraday's law, Lenz's law, and Newton's second law. So some assumptions that we can make for this lab is that the bar magnet is a magnetic dipole, the air resistance is negligible, and aluminum foil acts as a non-ferrous conductive tube. That's important for this lab. Experiment-wise, the system would be the aluminum foil tube and the bar magnet. The surroundings is everything else. And our initial conditions will be treating the bar magnet as a magnetic dipole. Procedure-wise, we need to assign the north pole of the magnet with the magnetometer app, drop the magnet into the tube, record the time it takes for the magnet to exit the tube, and then repeat that 5 times. Here's the data that I got from doing this experiment. The tube length ended up being 0.35 meters, the tube width 0.008 meters, the inner radius 0.021 meters, the radius 0.029 meters. The mass of the magnet was 0.025 kilograms, calculated a mu of 2.64. And here are the 5 drop times we had. Here is the glow script model and the initial conditions that we used here. You can see where the tube length, tube width, tube radius, where all of that comes in here. And then our mass is down here and our mu is down here. So coding for the tube and the bar magnet, here's the rest of it. And you can see through here we have our computations being done. So for the model, this is our tube over here. And through here we can see the velocity versus time graph charted with all of our data. So some sources of error in this could be that the timing could have been off when starting the timer and releasing the magnet, which would have affected the calculations in the lab. And one of the big things here is understanding the simulation. The intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current and which counterclockwise. So we know that red is counterclockwise, blue is clockwise. What happens to the dynamics of the system when you flip the magnet around? The direction of the B net would be opposite if we did that. How does the total time and tube of your real world system compare to that of your computational system? How might the computational system be more accurate? The experimental, we got 1.304, computational 1.044. If we did more and more trials, I think we could expect the experimental to get closer to the computational because the accuracy would be higher. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? So at the start, there's a large velocity due to the force of gravity. During, the gravity and the magnetic force are equal. And at the finish, the force of gravity is the only force acting on it. And for questions, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? Induced current would increase and the magnetic force would increase, so therefore the fall time of the magnet would take longer. But what if there were holes or slots cut into the tube? How would this affect the ring currents in your model? The induced current would decrease, the magnetic force would decrease, and therefore the magnet would fall faster and it would take less time. That's all I have for this lab today. Thank you all for watching.